Welcome back, everybody. Welcome back to the channel. So today we're going to be continuing where we left off with parsing the virtual machine or creating our virtual machine. So we've made it down to here where we're ready to start our application. Now, what we want to do is we want to create what's called a create virtual machine function. This is going to be inside of our virtual machine.cpp, and we want to create what's called a virtual machine. This is going to represent the data structure that is going to represent our actual virtual machine. So what we want to do is just create this class. Now, I mean, there's tons of stuff in here. We don't really need to care about this right now. Now, here I will explain something though. These are what's called frequently used classes. And these classes are assigned, if I go back to our create virtual machine function, these classes are created or accessed down here. And I call a function called resolve class. Now, we need to build a bunch of stuff before we're able to actually resolve classes. But basically, this is why I have my dependencies file in the actual Sharp standard library, where I basically say, hey, these classes cannot be obfuscated. So where was that at? That was in platform, dependencies, yeah. So like all these various different classes are classes that are used by the actual virtual machines. This is where the rubber meets the road, where we kind of pretty much see how everything works. So let's just go into here. So once we create our create virtual machine function, like I said, you want to create a class called virtual machine, and you want to create a local variable called VM. And I think actually this local variable is defined as I think it's defined as an extern at the bottom. So once you create, yeah, that way, if we want to access the virtual machine from a different file, we can always do that. So down here, we want to pass in the executable, and that's it. We don't care about like parameters or arguments or anything. We just want to create the runtime system. So the first thing we're going to be talking about is the executable. And with the executable, we want to create this process exe function. And what that's going to do is we're going to pass in the exe, and we're going to basically process the executable. Now today, what we're going to talk about is the manifest or processing the manifest version of the exe. That's the easiest part. But my executable, as you know, I mean, there's a lot of stuff in here that we're going to be processing, and there's tons of errors that we could potentially run into. So first, what you want to do is before or after, I guess, you create your process exe function, you want to create a bunch of define statements in an exe.h or the header file for the exe. You also want to write a definition for the process exe function so you can call it in the virtual machine. And you also want to put a extern to the exe error message. So once you do that, then you also want to create these errors. So we have various different errors as we're processing an executable, and I actually do use these because when we're building our language, it may seem easy now where I'm like, all right, I've done all this stuff, here's how you do it. But in reality, that's not the case. When I'm building this language, it is so complicated, and there's so many things that just need to go correct and need to just work together in order for everything to just work flawlessly, that there's so many components that can go wrong. There's too many points of failure. So at this point, what I do is as I'm processing my exe, I have all these different errors that may have resulted in something bad happening. Like the file could be corrupted, I have an unsupported file version because that's a thing. I do upgrade my file versions over time. And basically, what a file version represents is every time there's a new iteration on the programming language, I have to modify the executable to support that new feature. Now, because I'm at such a advanced point in my language, this is probably not going to happen again, but it's just something to think about. And then there's others. You can write them down, and here are the values. These values don't mean anything, so you guys can put whatever you want as the values, but yeah, that's what I have. So if we go back to the executable, now before we get into this, right, because I don't want to just show you some code and like you don't really know what the hell's going on. This is how my basic layout of my executable file is going to look. Now, as I mentioned before, I have a custom executable file. This is not something that is based on anything. I just made all this stuff up because I can do that. It's my own language. You guys can also make up your own stuff as well. If you want to add stuff, if you want to remove stuff, depending on how complicated your language is, you can always do that. But this is what I have. So I have what's called a signature. Now, with your file, this is also used with other interpreted languages. So Java actually does this. Java calls it a digital signature. And what this digital signature represents is this is a string of just a couple of characters that represent the I guess, key, quote unquote, doing the bunny ears, uh, to access the actual executable. So when we're actually running this, our file needs to have these specific set of bytes at the very beginning of the executable file for it to be ran. That ensures that this is an authentic executable file. But with those signatures alone, I actually take it a step further and ensure that we do have an executable file. I add onto that, after the signature, what's called a data offset. What a data offset does is it's just a string of zeros. So it's a string of bytes of zeros where it's basically a filler. So when we actually start processing all of the other various things in our executable, if it's an authentic file and once we get down to processing the manifest, it should just work flawlessly. There shouldn't be any errors. So this again is another way for me to ensure that yes, even with the data offset, it's still the correct file that we are processing. Once you do that, then I have what's called a manifest. The manifest is going to represent all of the basic information about your application. So I made up this because of Android. I'm an Android developer. So when you're actually developing apps in Android, you have what's called a compile SDK version, a target SDK version. You also have other stuff as well. I don't want to really get into it. This isn't an Android channel. But basically, when you have a manifest, you put all of the information in there that is important and specific to your actual application. So if I go back to here, let's actually go to, I think it's called manifest. Let me do a search, M-A-N-I-F-E. Oops, I messed that up, M-A-N-I-F. Yeah, so it's called manifest, and the manifest holds all of the very specific, application-specific information. So it holds, how many function pointers do we have? How many, what's the name of our application? What's the version of our application? Is our application debuggable? What's the entry method, meaning what's the main method of our actual executable? What's, how many methods or classes do we have, and as well as other data as well. So that's kind of what the manifest represents. It's just all the basic preliminary information. Then we have what's called the symbol table. The symbol table basically is what it is. It represents symbols in our actual programming language. Because of the way that my programming language works, since it's an object-oriented programming language, we will have multiple references to symbols in our symbol table that haven't been processed yet. So I do have a solution for that, so we'll see that later on. But basically what a symbol table represents is all of your fields, classes, functions, everything. So any symbol that we could have in our programming language and in our executable, that is what's in here. We also have the code section, pretty self-explanatory. It's just all of our functions and all of the code that is inside of those functions. Then finally, we have what's called the metadata section. The metadata section is basically going to represent all of the data that's going to be used for debugging purposes or for error reporting. So if your application is debuggable, you're actually going to have the source code literally injected into this metadata section. If we are not debuggable, then you're not going to have the source code, but you still will have some basic information like what file you were in at the time of the creation of the function, as well as what line was the function defined on, and a bunch of other stuff in there as well. So we will still have basic information, but again, as you guys remember, everything can be obfuscated. So we can obfuscate the symbol table, we can obfuscate the metadata section, because files can be obfuscated and functions can be obfuscated and everything. So, I mean, this could be completely gibberish if we actually put the obfuscation mode on. So with that out of the way, let's actually look to see what we need to do. So first, what you're going to want to do is create what's called the manifest data structure. And this is representing, again, your application info. And let's see, do I have a reference to that? No, it doesn't look like I do. Okay, so you want to create your basic constructor, which calls init, which just initializes all of these data sets. So we're going to have function pointers, again, application and version. Now this uses a runtime string. The reason why I'm using this versus just a C++ string, I've had issues in the past with using standard C++ strings when it comes to allocating memory. It's been a nightmare. So I just made my own string class, and it's called a native string, and that basically represents a string in C++. So that code is located in the, where is it, in symbols, and then string.h. So if you guys want to copy this header down, you can do that. You can also use strings as well, but I'm just warning you that when we start allocating objects and data structures, you might start to get seg faults in your actual code if you don't allocate the strings properly and set them up. And this is also kind of attributed. I've had tons of seg faults in my language before, so this is a way for me to kind of curb those because I didn't really know what the heck I was doing. Those seg faults aren't there anymore because I've greatly improved the language, but I just left this code in because, yeah. So let's go back to manifest. So you want to create your application version, whether or not it's debuggable, our entry method, methods and classes, our file version. This is the integer. So I think there's two different versions. I'll see what that means in a little bit. And then there's the target. We have our source files, and this is the target virtual machine, by the way, that we're going to be targeting. So as we build our virtual machine, we may have different target versions, and we can target which ones we want to run the executable on. We also have how many source files we have, how many strings we have, how many constants, and thread locals. So with all of that out of the way, let's actually look at the executable. Now here, I'm going to take this and kind of make this a little small so we can kind of see it and just kind of go through the code side by side. So when we're actually looking at this, we're going to check to see if the file exists based on the executable that we passed in here. We want to create what's called a file buffer and these two variables. Now a file buffer, again, that's in my file class. You guys can copy that down. That's in the util and file.h. And this buffer just basically represents data inside of a file. So once we have that, then we want to basically read all of the data and put that data into this buffer. So we pass in the C string of the exe and read all the data inside that file. Then we check to see if our buffer is empty. If our buffer is empty, then we say executable file of whatever is empty. Obviously, you can't have an empty exe. And then we return the appropriate error here as well as here. Then we want to validate the authenticity. So now we need to start checking that signature that I was talking about previously. We need to make sure that this is an authentic executable file. So we pass in the buffer and we basically just check to see if the exe at the current position, so I have this current position local variable here or static variable, and then I also have an error message and a temp string as well. So what I do is I check to see if the current position, I plus it because this is going to be the cursor of where we are in the file throughout processing the exe, is equal to the file signature. So if the first byte inside of our file is equal to file signature, this value is 0x0f. So again, these values are arbitrary. However, despite them being very arbitrary, you have to make sure that, so I have a ton of things. We'll go through each of the defines as we kind of approach them. I don't want to just go through them all at once. But as we're building these define statements, you want to make sure you're not stepping on your own toes because you want to make sure that each of these like digital signature, things that represent different sections in our executable, like the symbol table, the string table, which is another thing I actually forgot to add in here. So yeah, I also have a string table, a constant table, the data table, which represents the code section, and then the meta section, which is the metadata section. But as you notice, all of these values are different values. Like none of these are the same, so just make sure you do that. After that, we want to check to see, so we want to do a string forward. And this string forward is just a function which takes the buffer, the begin, and the end. And I basically take the current position and I blast it forward 3 characters. And I check to see if that is equal to SEF. And if so, then I say current position plus gets 3. And then I plus the zone offset or the, what did I call it? The data offset. Yeah. Otherwise, if that's not true, then I return false. So we have our initial signature to make sure it's a sharp executable. Then we check to see if the next 3 characters after that is equal to SEF. That is short for sharp executable format, just like ELF, which I don't know what it stands for, but yeah, it's kind of the same thing. Once we have that, then I check to see if the file's digital signature matches what I'm expecting. So the digital signature are consisting of 3 different characters. Now again, so I guess it's a little bit different. So it's not exact. I mean, this is supposed to be like a high level. This isn't supposed to be exactly how the executable file is formatted, but this is just kind of a bird's eye view. So I use 3 different bytes to signify that this is in fact authentic. So I have digital signature of 1, 2, and 3, which is 0x7, 1b, and 0xc. So you can copy those down if you want to use the same signatures as me. And yeah, so I just basically check to see if the exe at the current position, and I just plus it for all of those, and then I return true, otherwise I return false. Once we have successfully validated the authenticity, then if it's false, then we say error file executable cannot be ran, and we say file not authentic. Otherwise, so now we're basically past this and past this. Now we're at the manifest section. So this is what we're going to be going over today. So at the manifest section, what we do is I basically get the current flag at buffer at current position of whatever, plus the current position. I say processed flags. Now, as we're processing our manifest, to again make sure that we're processing an executable safely, because if we're not careful, we can actually crash the virtual machine if we process the executable incorrectly. So we'll see what the process flags does in a little bit, but we want to have a couple different characters. So if our character is a 0, 0xa, now if I go here to, where is it at? ASCII. So I use this website called asciicode.com, and this is kind of how I came up with the format for my executable. You can actually see down here it has all the different number values of the decimal, octal, and hex value of each of these different characters, and I use this to basically generate the format of my executable. So if I go back, what is it? So 0xa, I believe that is, let's see, 0xa, it's right here. So 0xa is a new line. So if we are 0, a new line, or what is the other one? 0xd, which represents the hex value of 0xd of carriage return. So if we have any of those values, then we want to, or end of header, EOH, which is 0x3. So EOH represents the end of the section. We want to basically just decrement how many flags we've processed, and then we'll process that information down here. Now, one thing I will mention, for each section that we process in this executable, I have what's called a end byte. What an end byte is it's basically the final byte or the nail in the coffin that says, all right, this is the end of that section. Once we've processed that byte, then we jump to processing the next section. So for the manifest, I have what's called a EOH, or end of header. If I scroll down here to processing the symbol table, what is it? End of section. Yeah, so I have an EOS, which has a value of 0x1d. So yeah, just keep that in mind. That's how you kind of keep track of where you are in the executable and, control the flow of things. So we literally just go down the list. So I literally have from 0x2 all the way to 0x1c. So I have from 0x2 to, I think, 9, and then I skip a couple different numbers from then on out, because some of these values represent other pieces of data that are inside of here. And again, you don't want to overlap any of this information. So you want to be very careful with that, because some of these symbols do mean certain things. So you just want to keep that meaning synonymous with that value. So yeah, I basically set up all my manifest values. For the first one, I get the application by getting a string, and I pass in the buffer. What I do is I return a native string, and I pass in the buffer and the length of that string. Now the length is going to be -1 by default. And the reason why is because, if you guys remember, as we're processing information, we're expecting there to be certain symbols to mean certain things. So I'm sure some of you are wondering, well, what if we process a string and we think that we're done processing that string, but instead the user just put some illegal characters in there? So what I do is I basically, when I get to the string table, I pass the length of that string so they can put whatever the hell they want in that string, and it doesn't corrupt the executable file. So that's why I do that, but let's go back. So we free up our temp string, and this temp string is what we're using to facilitate returning the value. I just reuse the same native string value, and I basically check to see if the length is not equal to -1. Then I just go and process the string for that length. So I plus get each byte in the data or in the buffer, and then I just add those values, and I plus the current position as well, because of course we have to keep it advancing. Otherwise, if it's not equal to -1, then I do a check to see while the current position is not equal to nil, meaning while the current position is not equal to 0, then I basically continuously process the string. And again, this is why I said as we're processing strings, well, if a user has a wacky string, they don't corrupt the executable because I just pass in the length of that string and then we're all good. So, and then I return temp string, and yeah, so that's how I get a string. I do this for version as well. For debug, I check to see if the current token is equal to 1, and that's going to be either true or false for the debug boolean. I also have the entry method, which calls a get I32. Now, this is pretty complicated. When we're actually processing information in our executable, we're going to have to break up our data. So if you remember, so if we have a 32-bit, that is broken up into 4 consecutive characters, because if you think of 8 bits per character, 1, 2, 3, 4, 5, 6, 7, 8, our 32-bit number is going to be 4 of these actual values. So we have to break up that 32-bit into these 4 individual values, and then once we get to the executable side, we have to basically pack those data values back into a single 32-bit number. That's kind of how it works on my executable side. So I have what's called a set I32, and I pass in W, X, Y, and Z, which represents each section of that 32-bit number. So I I mean, this uses bit shifting, so I don't really think I have to go over this too much. If any of you guys are curious about bit shifting, you can always look it up on YouTube. But I'm just going to be honest. If you want, you can just head over to my, where is it at? That's in my lib runtime exe.h, and you can just copy this code down. This is something that if you're going to have a programming language that's going to be a 32-bit programming language, then you can basically copy this code down and use this however you want. And this code here is actually used by my compilers. And of course, we'll see this later on in the YouTube series when we actually use this code. But yeah, that's kind of how that works. So if we go back, so I basically build a 32-bit number by getting the current token, the one after that, the one after that, and the one after that. And then I add the current position to an exe byte chunk. And that's just 4 bytes of data, and return I32, which is the 32-bit version of that piece of data. So let me remove this. Why is my computer moving so slow? Okay, so if we go back, where are we at? We were at the manifest. So once we get the 32-bit version of the entry method, and again, also another reason why I do this is, let's say the entry method's address was I don't know, we had a million functions or something in our code base. Well, a million is a lot of characters. I mean, that's 1, 1, 2, 3, 1, 2, 3. So that's a total of, let's see what that is. That is a total of 7 characters. So instead of it being 7 characters, I would end up effectively lowering the size of my executable by basically passing the 32-bit number value and breaking it up into 4 characters to represent that 1 million value. So that's another benefit of using this data structure here, or this form of, processing a 32-bit integer, because it saves size on your executable. So that's another thing you want to think about. So I also do all of this for the methods, classes, file version, the target. Now I use what's called parse int for others. And what parse int does is it does what you think it does. It just basically parses an int. So I get a string, and basically what this does is so let's say we had our 1 million example again. We would have at the end of that string a char. Whoops, we'd have at the end of that string char of 0. That's basically going to represent what the end of the string is, and then we'll just basically get the C string from that value, and then we'll just convert that to a long. So I use this function in the case where most likely the data that is returned from the number is less than 4 bytes. So if our number is less than what is it, 9999, if it's less than that value, then I use parse int, because there's really no benefit, because potentially I could have 999, and then therefore I have a smaller executable because I don't use all of those bytes. So I use that as well. So if I go back, the target is going to be the target version of the virtual machine. So I don't build virtual machines very often. Currently I only have one target, so it's going to be a 1 character number. So that's why I use that. Then we also have source files, which all use get int32 for source file, thread locals, and constants. After we process all of that data with all of my various different values for each manifest flag, I check for a default, and if it's none of these, then I basically just error out and say file whatever may be corrupt, and I say corrupt manifest. And then once we're done with the manifest, then I basically say current flag is equal to end of header. And again, if you remember up here, if the current flag is equal to that, we decrement the process flags and we break. So if the current flag is equal to end of header. After that, we want to check to see if we have a valid file. So we want to check to see if the manifest version is greater than the minimum file version. So if the file version in the virtual machine.manifest is greater than 4. So I have various different file versions. I'm on the 4th iteration, so this is the 4th time that I've modified and switched around how the executable file is processed and formulated. So I definitely do that because I do have some old files up here from like older formats. And if I executed one of those, I would probably crash my virtual machine. So I just basically make sure that I continuously upgrade the file version. We also check for the file version is less than or equal to the file version. So I have what's called a minimum file version and a maximum file version. And both of these values, I think, are just 4. Yeah. So I have both of those, and then I check to see unsupported file version of whatever. Sharp supports file versions from minimum dash maximum. That can be processed. Are you possibly targeting an incorrect virtual machine? So this is where it gets into virtual machine targeting. I also check to see if we've processed the amount of flags and header size. So when we process our manifest, I know that specifically I have a X amount of things that I need to process in here. If we have less than those that we've processed in the manifest, or we have more than those, obviously that's an issue. So we don't want that. It has to be exactly the amount of data that's supposed to be in our header. So it's 0xc, which if I go here and I go to my programmer, I go to C, that is exactly 12 items. So if I have 12 items, then we're good. Otherwise, I say corrupt manifest. Now, this code should be actually above here, in my opinion. So what this does is this basically checks to see if the, oh, let me actually put this one up here as well. So what this does is it basically checks to see if the target is greater than the current build version, and the build version is the version of the Sharp virtual machine that I'm running, and that is version.alpha. Now that is located inside, I have no idea where that is. Alright, so that is defined inside of my std imports. And that is basically, I mean, you don't have to define it here. It'd probably be best to define that inside of the exe file, but I have mine defined here. I basically create a data structure of Sharp, and I, have 2 versions. Now, this is the base. This is the original first version of my own virtual machine that I created. That's kind of when I started to get really serious with programming this programming language. That was back in January of 2017. After that, I also have an alpha, which is the current version that I'm running, which is version 2, and that started in January of 2018. So there's that. So that's the actual version. So if the target is greater than 2, then we say unsupported build version. And then, of course, we do this checks, which we already went through. So that's going to be it. We've successfully processed all that we need to do. So we're now at the symbol table part of the executable. So we've done all of this part first, and then we got just this part left to process. So hope you guys enjoyed the video. As usual, if you have any questions, as always, put them in the comment section below, or email me at devcode.channel, that is in the description. And of course, if you guys would love to help support the channel, you can always head over to my GitHub repository at andrewdevcd/sharp. And when you do, definitely watch, start, and fork this repository. That gives this language a lot more visibility and let other developers know this language exists. Also, if some of you guys are curious about what I do on a daily basis, you can head over to the remastered branch, and I write some pretty wordy commits so you can kind of get a gist of what I've been up to without really having to look too much in the code. Also, if you're curious about maybe some of the stuff that I've done in the past or stuff that I'm looking to add in the future, you can always head over to the docs folder, and in there's 2 main files. There's the change list, which is all of the old stuff that I've done in terms of updates, and the roadmap file contains all that information. as well as new stuff that I'm looking to add in the future. So hope you guys enjoyed the video. As usual, if you're new to the channel, definitely consider subscribing, and until next time, I'll see you guys later.